Welcome everyone. Most of us, when we think about linacs or try to learn about linacs, we're very quickly bombarded by a huge amount of details. And let's face it, most of these details are very boring. And so we end up thinking of the linac as something that's boring. And really what's happening is that we're not seeing the forest for the trees. And so what I'm going to try and do today is go over the big ideas of the linac without getting lost in the details and hopefully convince you that it really is super cool. One example of a result that I'll be going over is geometric scaling, and it's something that is very weird and surprising and central to linac design, yet it's something that most practicing medical physicists are only peripherally aware of. Once I dive into it and show how it comes about, you'll see how cool just this one idea is. The goal here is to accelerate electrons. Well, there's already technology that does this, and you don't even have to go far to find it. It's the old X-ray tube from diagnostic medical physics. The problem is that this only gets you up to 0.1 MeV, and we want to get all the way up to 20 MeV. And you cannot readily hold off millions of volts in a single gap. Well, one idea, which we'll label multiplication, is that if you have an accelerator that gives you some amount of energy gain, let's say it's 0.1 MeV or 0.7 MeV or whatever, you can make multiple copies of this accelerator, string them together, and as long as you can apply this string of accelerators to the same electron beam, you can multiply your energy gains and reach higher energies. For this to work, electrons need to travel freely from one accelerator to the next. Right now, this is not possible because the accelerated electrons get their energy by contact in the cathode. They're not free, they're tied to the cathode. So the next natural idea here is contactless transfer of energy. We need some way of remotely transferring energy to our electron beam without touching the electrons so that they can continue to travel freely from one accelerator to the next. Now here comes the plot twist. Even though idea 1 and idea 2 are perfectly logical and make perfect sense, they were actually subconsciously planted or suggested to us by a small background detail in our diagram of the X-ray tube. Can anyone guess what that background detail is? If you guessed the step-up transformer powering our X-ray tube, then you guessed correctly. So how does this transformer suggest ideas 1 and 2? Well, a step-up transformer multiplies voltage on mains power, which is shown here as the primary coil on the right, and outputs higher voltage on the secondary coil, shown here on the left. And the multiplication is achieved through multiple turns on the secondary coil. And multiplication is idea 1, so that's that. Furthermore, energy in a step-up transformer is transferred from the primary coil to the secondary coil without contact between the coils. So we have contactless transfer of energy, which is idea number 2. So the bottom line here is that this transformer, with some modification, can serve as the blueprint or the mental picture for what our linac is going to look like. If we can make a list of all the things that survive the analogy, that don't get changed, and the things that are modified, then this list can point us to what our linac is going to look like. First item in the list is something we already touched on and explained, which is that electrons in the secondary coil will now need to be freely traveling electrons. Right now they're tied to a conductor, and that's something that will need to be modified. Second item in the list is that we can keep electrons in primary coil inside conductor, so that's something that is not changed. Now, quick side note before I move on to item 3 in the list. I will be referring to the transformer's voltage gain or voltage multiplication factor as the transformer's multiplication efficiency. This is certainly not standard in transformer world, but I'm not really in transformer world, I'm really in accelerator design world. And in that world, when we think of efficiency, we think about maximizing what will ultimately correspond to the voltage across the secondary, meaning the numerator in that voltage multiplication factor. And because the notations between these two worlds don't always match, I will have to ask you to forgive me for abusing the notation in transformer world because I'm prioritizing notation in accelerated design world. Third item in the list is that we're going to have to throw away multiplication efficiency momentarily. We'll come back to it later, but what do I mean by multiplication efficiency? So the step-up transformer gives us a ratio that is larger than 1 of the voltage in the secondary coil to the voltage in the primary coil. And the reason for that is because that ratio is equal to the turns ratio, the ratio of the number of turns in the secondary to the number of turns in the primary. And that equality is based on Kirchhoff's law, which will be flying out the window here because we're going to be dealing with electrons that are traveling close to the speed of light. We're going to be at timescales at which Kirchhoff's law doesn't apply. So momentarily we'll be throwing away multiplication efficiency, and what that means for us is that we will simply have a number of turns in the primary that is the same as the number of turns in the secondary. This 3-item list that we've created points us to the third idea, which I'm calling resonant cavities. And what this idea is that we're going to be replacing this string of X-ray tubes, this mental picture of a string of X-ray tubes that we drew earlier. We're going to replace that with a string of conducting cavities. And what I'm going to do now is go over why this idea fits perfectly with the 3 items in the list that we've created in previous slides. So first item in the list is electrons in secondary coil will now need to be freely traveling electrons. In this new picture that we have, the electrons in the secondary coil will be represented by a beam of electrons that is traveling freely along the central axis of this string of cavities. And so one turn on the secondary coil will now be represented by an electron beam bunch flowing synchronously across a gap of 1 accelerator cavity. Second item in the list, we can keep electrons in primary coil inside conductor. So in this new picture, one turn on primary coil becomes oscillating current flowing on internal surface of the same resonant accelerator cavity. The third item in the list you'll remember is simply the fact that we'll have the same number of primary turns as we do secondary turns. And what that corresponds to in the new picture is simply that the number of cavities will be equal to the number of gaps seen by the electron beam, which is obviously true. Okay, now let's step back and let's try to see if we can recover multiplication efficiency. And already you have a clue as to how we're going to do this. And the clue is the word resonant and resonant cavities. So clearly we're going to try to recover multiplication efficiency by leveraging resonance. And the first step for doing that is to define as accurately as possible what we actually care about when we think of increasing the efficiency of the linear accelerator. And we have 2 starting points for doing this. One is the quality factor of resonance, and the reason, if nothing else, the reason why that's a good starting point is simply because that's a familiar quantity for someone who's been introduced to resonance. But it's really more than that. It actually is an okay ratio in that it does actually positively correlate with what ultimately we care about. It's just not the most accurate representation of what we care about. So we're going to tweak it in part by marrying it with the other starting point to finally arrive at our definition of efficiency for a linear accelerator. And the other starting point is simply what we previously called the multiplication efficiency of a transformer. That was our own terminology, we made it up. So let's start by looking at the denominator of Q, which is P lost. This is the power lost on the internal surface of the cavities. And what we want to have in the denominator are things that are bottlenecks. So what does this correspond to? This corresponds to the power that we ultimately have to supply the accelerator structure in order to make up for the losses. In other words, the power that's driving the accelerator. And as we'll find out later, this is actually difficult to obtain. It's hard to get to drive the accelerator at high powers. We'll come to that point later, but for now, it is certainly a bottleneck, and so it's going to be carried over to the denominator in Z. Now let's look at the numerators of these 2 starting points. The numerator of the quality factor is the power that's sloshing back and forth in the accelerator structure. And while that does positively correlate with something that we want to increase, what's more accurate than that is the numerator on the right, which is the voltage across the secondary, which in our analogy corresponds to the accelerating voltage across gaps. This is the voltage that the electron beam sees as it's crossing these gaps, and the higher that voltage is, directly speaking, linearly and directly speaking, the higher the energy gained by the electron beam, which is exactly what we care about. And so what we're going to carry over to the numerator in z is going to be the accelerating voltage. Next thing we'll do is we'll add a factor L in the denominator corresponding to the length of the whole, the entire accelerator structure. The reason we do that is that it's not enough to care about just the energy gain per power supplied to the accelerator structure if your accelerator structure ends up being extremely long. The last tweak we'll make to this factor is that we will put an exponent of 2 on top of the accelerating voltage. And the reason we do that is because without this exponent of 2, this factor is dependent on the amplitude with which we're driving or powering the accelerating structure. And we want this factor to be intrinsic to the accelerating structure, meaning not dependent on how we're powering it. And so once this exponent of 2 is introduced, this factor becomes intrinsic to the accelerating structure and is therefore nice enough to get its own name. Henceforth, you can either refer to it simply as the efficiency of the accelerating structure, or you can call it the shunt impedance per unit length. Either way, this is the factor that we will be interested in increasing or blowing up because it's the efficiency of our accelerating structure. And that is what the next idea is going to be all about. Idea 4, geometric scaling. This is the idea that's referenced by the title of this talk, by the way. And very simply, what we'll do is we're going to be shrinking or scaling down all length dimensions, including the wavelength with which we're powering the accelerating structure. And given that we're going to be scaling down or reducing wavelength, this means we're going to be increasing frequency. So all the length dimensions are going to be reduced, the wavelength is going to be reduced, and frequency is going to be increased, all in proportion. And what we'll do is look at how this shrinking, this geometric scaling affects the accelerator's efficiency. Now, before I go through with this, I just want to pause and comment on how strange this is. We're basically saying that we are going to get more out of the accelerator, more efficiency by shrinking it, which is strange. But what's stranger is the consequences of this. As you see in a moment, what this leads to is an efficiency singularity, so to speak. Now, of course, this is mitigated by the fact that we're making a whole bunch of ideal assumptions, and these ideal assumptions will break down well before we get to anything like an Armstrong accelerator. But nevertheless, this is strange and interesting. Okay, let's start with accelerating voltage. You can think of that as the electric field seen by the electron beam multiplied by the length over which they see it. And therefore, you see that it's proportional to the first power of length. Power loss is power that's lost along the internal surface of the cavity, so it's going to be proportional to surface area times the resistance in the surface of the conductor. And surface area is proportional to the square of L, so we have L squared times the resistance in the surface of the conductor. And the surface resistance itself is proportional to the square root of the frequency. I'm going to just take that as a given, I'm not going to prove it here. And the frequency itself, of course, is inversely proportional to length. And so what that means is that the surface resistance is proportional to 1 over the square root of length. Now put this all together and you do see that efficiency scales as the inverse of the square root of length, meaning it blows up as we shrink the accelerator unit. So just to see this strangeness in action, we're going to take a concrete example. Let's say you have an accelerator structure that is a string of n cavities. We're going to call G subscript T the total energy gain of the whole accelerator. G subscript C is the energy gain per cavity, and N is the number of cavities. So you get GT equals N times GC. Now, we'll scale down cavities by a factor of 2, but we'll multiply N by a factor of square root of 2. Ignore the fact that you get fractional cavities here. We're just drawing a cartoon. And then you look at the total energy gained in the scaled version divided by the original version, and you see that that actually doesn't change. So we haven't changed the total energy gain. And then if you look at the length of the scaled version compared to the length of the original version, you see that we have actually shrunk it. So we shrunk the total accelerator without affecting the total energy gain. In other words, we have an efficiency singularity. So you can think of this geometric scaling result as a very loud invitation to not just make resonant conducting cavities, but makes small resonant conducting cavities known as microwave resonant conducting cavities. And one of the people answering that call was Hansen at Stanford. And so he went about working on these microwave cavities in the mid-1930s, and he bumped into a barrier, however. And this barrier had to do with the power he was getting from the power drive. So if you think of the energy gain is proportional to the efficiency times the power with which you're driving the accelerator. And by shrinking the accelerator, you end up blowing up the efficiency, but at the same time, for Hansen at least, that ended up shrinking the power he was getting from the power drive. And so Hansen had to wait until his associate, Russell Varian, in 1937, came up with the idea for a klystron. And the klystron is a device that gives you high power at the high frequencies required by Hansen's microwave cavities. So it solved the problem. Russell Varian told his brother, Sigurd, to go build it, and his brother built it in 4 weeks, supposedly, which is crazy. And the problem was solved. Now, one more thing I'll mention just to tie up loose ends here. Now that we're talking about the power required to drive these accelerators, if you look at the power required to drive these accelerators, and you look at the power that's in the outputted beam, there's a mismatch there. For the purpose of treating patients, you don't really need that much radiation. And so what ends up happening is that even though we do need high peak powers to drive the accelerator, we don't need that power to be high on average. And so what you end up doing is pulsing both the power that's driving the accelerator and also the gun that's shooting electrons into the accelerator. We'll get into these probably in later talks. This talk has been long enough as it is. If you enjoyed it, as they say, share, hit like.